Okay, so let's see. Here we go. New section for today. So last time we finished section 5.5. We're moving on with 5.6. This section is a lot of applications. I have to be mindful of the fact that this is a math class, right? And so when I show you applications, it is tempting. I do have a partial background in physics, and I do kind of get excited about the physics sometimes. But this is not a physics class, right? So I am going to try to focus on what I think are the most mathematically deserving topics with, of course, all these time constraints and other considerations in mind. So we might go a little bit more quickly through this stuff. Okay, so starting with the idea of the average value of a function. We're going to start off with an even simpler idea called the idea of a weighted average. And I'm going to start off that with a really familiar idea, which is how to average numbers, right? And there you go. Here's an example of us averaging, I guess you might say 6 numbers, right? But arguably also we're averaging 3 numbers where some of them get counted more than once, right? Depending on how you look at it, right? So now changing the way I've got that written down, of course I can write it like this and I can write it like this. And what's kind of neat about this is you notice that these numbers here, in how I have this very simple averaging of 3 numbers with, you might say, different multiplicities, right? These numbers here tell you how many times, in some sense, the number shows up. So the number 4 appears twice, and thus these 2's. And likewise for the other multiplicities. So with that in mind, these multiplicities being represented like that, notice that this is just a summation that looks like that in the numerator. And in the denominator, we have a different summation that, looks like that, where in particular these numbers, the multiplicities, right, show up like so. Okay, so this is just a convenient shorthand, a nice sort of compact representation of how to deal with an averaging of numbers when some of those numbers appear more than once, and thus with a multiplicity. Okay, with that in mind, now I said the term multiplicity because I was trying to represent the fact that these represent a count. How many times does this number appear? And of course, how many times something appears is always an integer. Okay, with that noted, notice that in this formula here, there's no particular reason why these numbers should have to be integers. No particular reason at all. So in fact, we don't usually call these multiplicities, we call them weights. And the idea is it's kind of like a multiplicity, except it just doesn't have to be an integer. Why should it have to be an integer? Okay, so this is called a weighted average. And it's used for a lot of different things. Y'all may recall in particular that it's going to be used in this class for how we compute course grades. Right? Your course grade is going to come from a weighted average of your various scores on various graded items, exams and such. Okay. All right, so now what I have here is just a quick example of a weighted average. These weights are not exactly the same as the weights for our course. Right? These are a little bit different. In particular, our final exam is only worth 30%. In this class. And then there's also the homework that's 7% and the attendance is 3%. Little micro deals like that, right? But as an example for a weighted average, just keeping it numerically a little bit more convenient, notice these weights go like that. And the grades in particular that Bob scored go like that. And notice that what we have then is all of this arithmetic is just kind of a fleshed out representation of this weighted average formula, where I'm literally stealing straight out of that formula right there, and arithmetic ensues. And as it turns out, this weighted average is this number right here, which of course is just a little bit under what you might call the stereotypical, the standard B, And so Bob would get a, it rounds up, and Bob gets a B. Does that make sense to everybody? Okay. All right. Okay. So we're going to now expand this idea to averaging a function. Now, a function is not a finite list of values. A function is infinitely many values. Right? Kind of a creepy idea a little bit. But all we're going to do here when we define the average value of a function is we're going to use size in the domain to be the weights. It's as simple as that. Size in the domain is the weight. So here it is. dx is the size in the domain. You see it's playing the role of weight. Now, there is an integral here. What's going on with these integrals? The main thing to recognize about integrals here is they are summations. And yeah, there's a limit involved and blah, blah, blah. But this is highly analogous to the formula that we were just looking at for a weighted average. And again, size, dx, representing how many in some sense of those values of x. Those sizes are the weights. Kind of like a multiplicity in a sense. Okay. So there you go. Now a quick observation is, of course, that denominator integral is super easy. And write that down to get a nice little streamlining of the formula. And here then is our efficient formula for how to compute the average value of a function. And the example here is just plug and chug. Y'all can totally do that one on your own. Okay. Now, analogously, thinking about how we adapted the idea of a weighted average to this continuum of values, right? Analogously, if you have a function of two variables, if you have a function of two variables, then size in the domain is now area instead of width. But so same basic idea. What we have here, this is a weighted average. Again, integrals are summations. This is a pretty much straight up rip-off of the idea of the weighted average. Again, using size as our weights. And again, very conveniently, this bottom integral, really easy to work out. It's just the area of your domain. You're literally adding up all the pieces of area. So that gives you the total area. And so again, we have a handy dandy little formula and an example where you can crank it out and find the average value of x squared there. How are we doing? Is everybody following? Okay. All right. What does this have to do with physics? So I'm going to start off with this idea called center of mass. Center of mass is a weighted average. There's different ways to think about center of mass. We'll get to a physics-y point of view in just a second. But it's the weighted average of position. So just as a get the ball rolling example, you'll see I have a couple of masses here. There's one mass. There's another mass. Hopefully no surprise. If we want to take a weighted average, what are we going to use for the weights? Well, I mean, mass is commonly confused for weight, so not an outrageous suggestion that we would use mass as our weights. Okay. And specifically, it's a weighted average of position. And so you see here the position, the x-coordinate, where are these masses located? Right, these x-coordinates. And all together then, the weighted average, this expression gives you that final value right there. Everybody buy it? It's just a definition. Now, a reasonable question comes up, why would I be interested in the weighted average of position? What is it about this concept that makes sense in a physical sense? And here it is, the physical tuition is that this is the balance point. If this mass here and this mass here were connected by a lightweight, I like to think in terms of like a little piece of balsa wood or something, something that's strong but doesn't really have enough mass to actually contribute on its own. This is where you would put your finger. The weighted average, the center of mass, is where you would put your finger so that it balances. In other words, the total torque is 0. As you could imagine, if you have your finger right here, oh, whoop, I'm sorry, wrong color, purple. If I had my finger right here, then this piece of mass is going to have torque clockwise, right? And this piece of mass is going to make torque counterclockwise, and they'll balance perfectly. Now, that is a calculation. That's something that, everybody should, again, this is physics at this point, so you don't have to, but if you just want to make sure that you've got a good feel for this kind of stuff, wouldn't be a bad idea to literally compute these torques, add them up, confirm that you get 0. Okay. All right. Okay. So, again, copycatting. Here's the sort of generalization. If you have more than 2 pieces of mass, if you have like a continuum of mass, again, we use the masses as the weights. We, again, are taking a weighted average of position. Position in general being represented by a vector, right? Then again, you'll notice that what we have here is our typical formula for a weighted average. And again, the denominator simplifies very nicely, right? So this is just the total mass. And so again, we get a lot of these formulas look a lot alike, right? And our center of mass, in general, for mass distributed over some region, is this formula right here. There is an eyebrow raiser in this formula, if you haven't noticed already. This is our very first time to do an integral of a vector. What's up with that? Can you do that? Is that legal? Right? I mean, we've seen nothing of this sort previously. Every integral we've seen up to now, the integrand has been a scalar. So what does it even mean to talk about an integral of a vector? And there's a wonderfully convenient answer to this question, and that is just to recognize that, there we go, that position has a bunch of coordinates. And let's just take this sort of one little piece at a time. What happens when you take a vector and multiply by a scalar here, right? dm is a scalar quantity. Vector times a scalar, how do we compute that? One coordinate at a time. Okay, fine. Then we're going to be adding up a bunch of stuff. How do I add up a bunch of vectors? One coordinate at a time. Right? How do I multiply a vector times a scalar? One coordinate at a time, right? So every part of this operation of computing an integral of a vector, every part of that operation is computed one coordinate at a time. And so altogether, taking the average is literally done one coordinate at a time, and you can see the result here then. This thing, well, here, let me do it like this. This thing is computed one coordinate at a time, right? So you're going to do an integral with the x1 coordinate in here to find the first coordinate of the center of mass. Second coordinate for the second coordinate of the center of mass, etc. Good news, it's exactly what we would sort of hope. Couldn't ask for an easier answer. Okay, so let's get our hands dirty and do one. Here we go. We're going to look at this upper half disk here like this. We've got mass distributed across that upper half disk. By the way, notice so the particulars, right? So the radius is A. The density is 1. That's just to make the algebra work out more reasonably on this. In general, you can't assume the density will be 1. It might be some odd function. But I will say that if you ever find yourself looking at one of these examples where the density is not discussed at all, there's no indication of there being a density, this is the sort of standard assumption if it's not indicated otherwise. Okay. So, density is 1, and here we go. Copying from above, we're computing the coordinates of the center of mass, right? The x coordinate of the center of mass, the y coordinate of the center of mass, one coordinate at a time. Copying right out of the formulas we were just looking at. Wait a minute. What happened to the dm? Right? How come these dm's turned into dA? What's going on there? Well, the relationship between mass and size, of course, is density, and in this case, very conveniently, can't assume this in general, but very conveniently here, density is 1, so dA is dm. Yeah? Yeah.
If it wasn't 1, would you just multiply it by the number?
Yep, whatever that, and it might be a formula, in which case you just stick that formula right in there. Yeah. Everybody good? Okay. All right. Now, you will notice this integral here, 0 by symmetry. I think I actually may change my lecture notes on this in future semesters and not have this written down, because then students just immediately see it, right? And I do want to have the sort of the dramatic effect of pointing out that when you find an integral that is 0 by symmetry, it usually does not announce itself, right? Most of the time, you're working some problem, and there's some aspect of it you need to know, and you write down some stuff, you end up with an integral, and then the integral's just sitting there looking at you, right? It doesn't say, hey, by the way, use symmetry, right? So anyway, heads up, right? Please always head on a swivel when you're working any sort of not only any sort of an application problem, but any sort of a problem that involves integrals. Just always be on the lookout for the possibility you might be able to use a symmetry argument. Because again, usually they won't announce themselves, and usually the statement of the question won't even suggest it. Right? So you have to kind of make the realization on your own. Now, I do want to encourage you, reminder, check these details. Remember, on the exam, we have an exam later this week, right? On the exam, you got to give me 5 particular checkpoints of the argument of how a symmetry argument works, right? So think it through, and the devil's in the details, right? Make sure that you can comfortably write down the argument that this integral is 0 by symmetry. Yeah.
So what should we do if we work it out, completely, and then get 0? Is that enough, or do we then need to use symmetry arguments?
Oh, if there's an integral that's equal to 0 by symmetry, but you don't notice that, and you just crank it out the old-fashioned way, then your penalty is you had to do all that work. Yeah, that's okay. Yeah, I mean, I could conceive, depending on the situation, depending on the wording of the question. I mean, one thing that I do have written somewhere is that the grading on an exam question is on the basis of various things, and one of them is clarity of thought. Case can be made that if you exert a bunch of effort computing an integral the old-fashioned way, and if it turns out that there was a magic wand, that you could wave, the case could be made that that work isn't really as good, right? Because it's way less efficient. And again, it's not about the answer, it's about the reasoning. Case could be made that maybe it might be a little bit less than full credit. But it wouldn't be much. It would just be a minor. It would be, I don't know, 19 out of 20? I don't know, something like that. Anybody else? How we doing? All right. Okay, sadly, this integral here, not susceptible to a symmetry argument. By the way, a really easy way to see that there is no hope for a symmetry argument there is that if you look at the integrand clearly in the picture always positive. Symmetry requires that it be negative just as often as it's positive. That's how the symmetry argument works, right? So no hope, couldn't possibly, and furthermore, by the way, also perfectly obvious from this observation here that the answer here must be positive, right? So how are we going to actually crank that out? Well, you got a bunch of options, and by the way, polar coordinates would seem to be a pretty good choice here. Might want to think about doing this calculation in polar. I like showing the students these two options here just because it gives me an excuse to talk about a particular sort of strategizing, you know what I mean, that I think is really useful sometimes when you're looking at these two possibilities and trying to decide which of these should you do. You don't have to actually write them down and compute them to realize which one's going to be easier. Sometimes you can look down the road before you actually walk down the road. And so, for example, let's just kind of look slightly down the road for this first example here. I see y dx, y being a constant because the dy is further to the outside. After I do this inside integral, I'm going to have y times something that involves that square root. And then I think, okay, cool, I can do a u substitution, and that'll make that integral work out not bad, right? One u substitution, pretty straightforward. On the other hand, let's try to strategize here. Very first thing I'm going to have to do with this integral, I'm going to do an integral of y dy. That's going to create a y squared. Into that y squared, I will be plugging this square root, and the square root disappears. And then I have a really easy outside integral. After all, it's just a polynomial, right? And so now I didn't actually do any algebra there. You notice, right? I just my hands totally off the screen there. So even though I didn't do any algebra, I'm already realizing that I like this one better. Just kind of looking down and seeing how, the algebra on this one's going to be very, very nice. Is everybody happy? Okay. All right. Okay, moment of inertia. This is another one of these things that's a really cool physics concept that I would love to spend 20 minutes on the physics background for why we care about this. I'm going to have to cut that down to just 4 or 5, something like that. The basic idea here is that we have an axis of some sort, and around that axis we have some object that is rotating, like so. And various parameters. You can keep track of where you are by how much distance you've traveled as you rotate. You can keep track by how much angle you've rotated. Of course, as you rotate in a circle, there will be a radius of that circle. And blah, blah, blah. Another thing you might want to do is ask as this particle moves, what is its kinetic energy? Right? Now, that's a physics concept. I hope you all have all seen some version of what kinetic energy is. It's actually there's a lot to say about that. But again, this isn't a physics class. But the classic formula for kinetic energy, 1/2 mv squared. And if you have a particle sitting here rotating around, no problem. That particle's moving with some velocity. It has some mass. Plug and chug. Here's where things get weird. If instead of a particle, if you have some lumpy solid, I always feel this compulsion to fill in completely. Okay, here we go. If you have this big lumpy solid like this, and that's rotating around, which by the way is a little bit more realistic, right? Real world, point masses are not such a common thing, right? We tend to have lumps of mass. The problem is this little piece of mass right here travels that distance in a full turn. In the same amount of time, this little piece of mass right here travels a much greater distance in the same amount of time. This little piece of mass here, sort of further away from the axis of rotation, is literally moving faster. It has a greater velocity than this little piece of mass right here, even though they're part of the same piece of mass, right? So if I wanted to compute the kinetic energy by way of this formula, perhaps, I've got a problem. What's my velocity? Do I use the purple velocity or the orange velocity? It doesn't make any sense, right? It's really not clear. Okay, so This can totally be dealt with. The way you deal with it is all of this work right here, which is some lovely physics, and it is actually mathy as well. We don't really have time for it. It's not really the point of what we're doing here. The point is that while you are interested in computing kinetic energy, instead of using this formula that assumes sort of linear motion, we can translate it into a formula that looks like this. That's assuming angular motion. So everything concerning this lump of mass going around an axis, it's all written and understood here linearly. Angularly. So for example, this thing right here, angular speed, sometimes called angular velocity, that's just angle per unit time instead of distance per unit time. So this angular speed, I think, is very reasonably understood as an angular analog of speed. Speed in an angular sense instead of speed in a linear sense. And now we observe, okay, well, we have this formula up here, 1/2 of stuff times something squared. Down here, 1/2 of stuff times something squared. I mean, structurally, these formulas are really, really similar. This thing here is an angular analog of that thing there that's in the same place in the structure of the formula. And it's just highly suggestive that we should think of this thing as being an angular analog of that thing. So the role that mass plays in the computation of kinetic energy in a linear sense, this thing, whatever this is, plays that role in the angular sense. So this thing, whatever that is what I like to think of as being an angular analog of mass. It's a little bit creepy, but everything fits if you think of it this way. So what is this thing? Well, it's this formula. That's just, again, how the algebra works out. And the term that we use for this thing here is moment of inertia. And it's a really important thing, really important physics concept to understand, because in the real world, and I know a lot of y'all are engineers, right? Well, stuff rotates, right? Wheels on cars, pretty easy, obvious example, right? Very important. And a tremendous amount of energy is rotational energy that's in the tires, the wheels, I guess I should say. So if you're interested in making your car more gas efficient, well, you got to account for all that energy, and well, this is a significant part of that energy, and this is how you calculate it, right? So the mass of a wheel is one thing. The moment of inertia of the wheel, also really, really important to being able to, to even play with these kind of things. Okay. So with all of that in mind, these are, whoops, go away. There we go. These are the things you need to know about moment of inertia. It's got a formula, typically written with a capital I, and intuitively we think of it as an angular analog of mass. Okay. All right, now there is a weird thing about this formula. Good news, bad news. Good news is this formula is pretty much always the same. No matter what axis you're rotating around, even if this is you'll see here I've got a triple integral. We were assuming we had a three-dimensional thing. Right? If you have a two-dimensional area with mass distributed two-dimensionally, no problem, same integral. It's just a double integral instead of a triple integral. It's always integral r squared dm. That's really all you have to remember. Integral r squared dm. Everything else is kind of packed into that formula. So the bad news, the one thing that is a little confusing, is that what this r is depends on the scenario. So for example, notice up here in this picture, r, it's not distance to the z-axis like in cylindrical coordinates. Well, not necessarily. It might be, but it isn't in general. It's the distance, rather, from wherever you are, whatever your x comma y comma z is, It's distance to the axis of rotation, not necessarily the z-axis. Okay, so keeping that in mind, I mean, here's a couple of examples. Now, again, sometimes you're lucky, and sometimes you are, in fact, literally rotating around the z-axis. And if that's the case, then this distance really is, square root of x squared plus y squared, just like in cylindrical coordinates. Sometimes you get lucky. But here's another example. We might be rotating around this line. Right? Totally different line. It's not even parallel to the z-axis. Conveniently, it's parallel to the x-axis. Yeah, nice. Right? That being said, this line described by those equations, this line, I can totally compute this r by recognizing that there's a very convenient little right triangle like that. And if you write down the Pythagorean equation for this triangle, your r turns out to be that. So different formula depending on what line you're rotating around. Everybody cool? Some students like to write down a finite list of scenarios that there's only so many lines that you can expect to be rotating around, and to sort of memorize that complete list of possibilities and memorize what the resulting r's are. I think that list is too long. I think it's a bad idea. I think you'll end up misremembering or confusing cases or something like that. I certainly have never done this in my life, and I never will. I don't trust myself to remember things. I do trust myself to understand and analyze. So I encourage you not to memorize a list of formulas. Again, here's a couple more examples. Right, a little bit different in every scenario. Here I don't have three-dimensional lumps of mass. Here I have two-dimensional lamina of mass. Right, and so that changes the formulas just a little bit, but it's always clear from the picture. Is everybody okay with that? Yeah.
Could you just explain where the x minus a comes from?
Yeah, sure. Right. So this this point. Let's see here. This point here. That's the point x comma y comma 0. Right. That's the point that we're going to be doing an integral over this region, and when you're integrating x comma y, that's how you keep track of where you are in your region. This line that we're rotating around, most importantly, has x equal to a, and so if I want to know the distance there, that distance is a purely parallel to the x-axis distance, so I can just look at the difference of the x-coordinates, and this one we're looking at x, here we're looking at a, the difference is x minus a. The only trouble is that it's not immediately clear which side of the line am I on, and so what I don't want is to end up with a negative value for distance. That doesn't make any sense, and so absolute values. Yeah. Is that cool? Everybody happy? All right. Okay, so let's see an example. Here we have a two-dimensional lamina of mass. There we go. Close enough. And I want to imagine that as rotating around the x-axis here. And as that rotates around the x-axis, it's going to have some sort of a moment of inertia. All right, so let's compute that moment of inertia. Excuse me. So, we have a formula. Integral r squared dm. Notice I write that down immediately. It's always that. And then you just have to kind of figure out from the context, what are these things? The r, what is that r? Well, here's my picture. Right? It's the distance from an arbitrary point, x comma y, down to the axis that I'm rotating around. This axis is the x-axis. The distance is just then this vertical distance, and it's y. Is everybody happy? what's the deal with this dm here? Oh, let's see here. I'll use blue. Mass is density times area. Density was given. So when I have density times area, the density is this. That's just plugging in what I was given. Area, of course, dx dy or dy dx, depending on your preference, depending on what's going to be the better way to slice this up, which of course we resolve by asking which would I rather solve for. Would I rather solve for y? Would I rather solve for x? And I'm looking at this equation right here and thinking I'd much rather solve for y. That's why I put the dy on the inside. And then it's all downhill from there. Everybody happy? Okay, so that's it for Chapter 5. And now we move on to Chapter 6. This is where the course gets a little bit more exciting. There's a lot of really wonderful parts of Chapter 6 and 7. The short version is that we're going to find ways to come up with various 2 and 3 dimensional versions of the fundamental theorem of calculus. It's going to have certain earmarks of the fundamental theorem of calculus, even though the context is going to be totally different. So anyway, it's wonderful mathematics. Okay, moving along. So here's a quick observation. Every integral that we've seen so far, there's been a nice convenience that we've sort of taken for granted. It's always seemed reasonable. But notice our domains that we've looked at have always been the same dimension as the space that they live in. And so, for example, in single variable calculus, we're looking at domains that are intervals. They're one-dimensional. And they live on the x-axis, which is one-dimensional. Right? Okay, likewise, now we go up to double integrals, and so we have regions in the plane. Well, the regions are two-dimensional. They're in the plane, which is two-dimensional. Triple integrals, solids, they're three-dimensional, and they live in a three-dimensional space. Always the same. Right? Well, doesn't have to be. What if it isn't? Right, so for example, here is a curve. This is an intrinsically one-dimensional thing. It has length. It doesn't have any area. It doesn't have any volume. It is itself a one-dimensional thing, and yet this lives in 2 dimensions. Lives in a 2-dimensional world. So here we have a mismatch. The domain and the world that the domain lives in, different dimension. And we have not made any consideration of what would it look like if I want to do an integral on one of these things, right? This is not a single variable integral as we've conceived it so far anyway, because single variable integrals happen on the x-axis. How do I account for the fact that this is all curvy and stuff, right? That way we don't have any way of, no single variable calculus class really addresses this. Okay, fine. 2-dimensional context, we'll just do a double integral. Can't. There's no area. Right? So this just doesn't fit. This is a square peg round hole kind of a situation. Everybody with me? So what we're going to do is we're going to actually create a whole new kind of a Riemann sum. And so, we've done this a couple of times before. We've found ourselves in new contexts and asking ourselves, what does it look like when you chop it up, add it up in our new context? And so we're just going to do exactly that. Forget about the kinds of integrals we have at our disposal. Let's just ask, look, if I take this domain and if I were to chop it up into a bunch of little pieces, such as, here's a little piece, right? If I were to look at that one little piece, how would I answer the question of what's happening on that little piece? And secondly, how would I then add that up over the entire domain? Right? It's just chop it up, add it up, like we've always done before. Now, on the little piece, these questions tend to be pretty simple, right? And keep in mind, we're talking about accumulating quantities. My favorite example is mass. I just find it very relatable, very familiar, comfortable, right? It's nothing creepy, right, or hard to visualize. Mass, it's, we're surrounded by it all the time. And if I have mass distributed across a piece of curve, well, how much mass is there in this little piece? Well, it would be mass per unit length times the length, right? Kind of a weird thing to think of mass as being distributed across a curve, right? Instead of mass being distributed across a volume, a three-dimensional region. But it actually makes loads of sense. So, for example, if you want to talk about a kind of let's say you have a 2x4. How much do 2x4s weigh? It depends, right? How long is it? Right? Longer ones weigh more, shorter ones weigh less. You would describe the mass of the 2x4 by mass per unit length. And the fact that it has a width and a height, that's always the same. I don't really care about that part. It's the length that's something that's going to change, typically, right? And so I want to think of the mass as being distributed across length. Does that make sense to everybody? Okay. All right. So let's talk about this quantity, Q, that we're interested in. Again, I like to think of this as being mass, but that's just for kind of visualization purposes. Because we were interested in mass, my integrand here is mass per unit length. But again, we don't want to pigeonhole ourselves here. We're not really actually tied down to this being specifically mass. This could be any accumulating quantity. And so, for example, if this was this could be a population thing. And so imagine that this is a bent metal wire and there's ants crawling all over it. Or maybe this is a river and I'm interested in the number of fish that are in the river, and I understand fish population by how many fish there are per unit length of the river, whatever, right? So this quantity could be anything. It could be population, in which case the integrand is population per unit length. Whatever it is, quantity per unit length times length gives me quantity. All right. And then, of course, I just add up over the entire domain. And practically speaking, by the way, how do we actually rubber meets the road? How do I turn the crank on this? Yeah, well, okay, we're going to have to worry about that. Right now, we don't know how to do that. Please don't be concerned right now with the question of how do we compute these things. We'll get to that in just a couple minutes. I just want to point out that this is a strategy for taking a question of an accumulating quantity distributed over a curve. And what would it look like if I were to say chop it up, add it up on that curve? Okay. Right. Okay, let's talk about notation real quick, and then we'll start actually practically doing some and worrying about computation. So I hope it comes as no surprise that adding up over your domain we represent with an integral symbol. Right, just like every other integral we've ever done. Right, so why not? Hopefully also no concern that delta S we abbreviate with ds like every other kind of integral we've ever done. So again, hopefully familiar. And then just whatever this function is, that goes in our integrand. Of course, you have to indicate what your domain actually is, right? This curve that you're adding up over. Right? Make sure to indicate that, and we do that as a subscript, again, as we've done before. So I think the notation is pretty believable. Okay. All right, so now the looming question, how do we compute? The first observation I want to make is that this is what I'm going to call an undesirable domain. I think that's pretty clear. It's a pretty weird domain, right? It's dimensionally undesirable. It's not because of corners. It's not because of the equation of the curve or something. No, it's really weird. It's a one-dimensional thing in a two-dimensional world. We have no experience with how to deal with that. Okay, so not our first time with an undesirable domain. Change of variables was all about how to get rid of an undesirable domain. And the way we do it is you view it as being an image of something, and then you use a pullback. Right? We're going to do literally that. Adapt it appropriately for the context, but it's going to be the same big picture idea. We're going to view our undesirable domain as being an image, and then we're going to pull back through that function. Okay, so here we go. Here is our undesirable domain. I would like to view it as being an image. Specifically, I want it to be an image of a, well, presumably nicer domain. The whole point, what we don't like about this is that it's dimensionally bad. So obviously, we want this new pullback, new domain to not be dimensionally awkward. So I want it to be just an interval on the t-axis. And we've done this before. This is exactly a parameterization. Right? If you have a curve and you can write that curve as being an image of an interval, that is a parameterization. So, step one, when you're going to compute one of these, terminology. When you want to compute one of these scalar line integrals, right? Step one, parameterize it. Okay. All right. Now, once you've parameterized it, great. What's the deal with the stretching factor? Keep in mind when you pull back, there's going to be a stretching factor. So, how long that little piece of curve is, and how long the little piece of the t-axis is that creates it. These are not the same. All right? I mean, parameterizations, first of all, there's lots of different parameterizations. And so we would not typically expect ds and dt to be the same. Why would they? So what's the relationship between them? What do you multiply by dt to get ds? Let me say that differently. What do you multiply by time to get distance? Well, how about distance per unit time? Speed. Right? And so that is, in fact, our stretching factor here. The thing that you do to dt to get ds. Right? What is it that you multiply by dt to get ds? It's speed, namely velocity's magnitude. Right? And that's our stretching factor. So that's what you have to kind of stick in there to make your ds something that you can write in terms of dt. Familiar? Kind of smacks of change of variables. Is everybody okay with that? All right. Okay, you'll notice everything else in here is just literally plugging in. So, for example, what do we do with the position here? So, like this point right there, that location, x. How do I describe x as a function of t? Well, that's what the parameterization does. The parameterization literally tells you position as a function of t. And so this is where I say we're just plugging in. I mean, that's there's no tricky curves here. X is a function of t. Write it down, stick it in there, nothing to it. Right? Okay. All right, now we can actually do some. And I always forget to, okay, one other little detail. This is a quickie. This is a mathematical kind of formality. This expression here, you can see the parameterization all over the place. In particular, there's the parameterization. There that I'm taking the derivative of is the parameterization. This expression seems, at a glance, to depend on that parameterization. Which means you would think, at a glance, that if I parameterize one way and somebody else parameterizes a different way, we might get different answers. But wait a minute, we're computing the same accumulating quantity. We're computing the same, we're trying to compute the mass of the same thing. How could we have an expression here that depends on the parameterization that we just make up when we're trying to compute something that is clearly not supposed to depend on the parameterization? So the good news is, surprisingly I might say, this is independent of the parameterization. It's not obvious that this is true, but it's very convenient that it works out like this. Any parameterization you use always gives you the same answer. Okay. So you don't have to worry about that. Alrighty, and now hands dirty, let's do one. Here's our question. We've got an irregular wire. The path that it follows is pre-parameterized for us, just to kind of get the ball rolling, right? Just to, one won't always have a parameterization given to you. But here we have the parameterization given. Here's how the mass is distributed across this wire. Notice it's not constant, right? So it depends where you are on the wire. So, weird little scenario. And with all of this given, we're going to compute the mass of the wire. We're going to compute the location of the center of mass of the wire. We're going to compute the moment of inertia around the x-axis. Various different things we're going to compute. And for reasons that you'll see in a second, I'm going to do all these computations at the same time. It turns out that they're all extremely closely related integrals. So real quick, let's see here. We have, mass. Mass is an accumulating quantity that holds the sum of the parts. That's this first line here. And of course, mass is density times size. So my first scalar line integral comes about just pretty immediately. Second, we are going to compute the center of mass. And I'm going to start with the x-coordinate of the center of mass, which is just that formula that I'm copying straight out of our previous discussion. And of course, as usual, mass is density times size. Okay. All right, so we find ourselves now with these two integrals. They look different. They have a tremendous amount in common. And so let me illustrate, first of all, what do these things all have in common? And let's see here. Here we go. They have in common you know what? Let me just go ahead and erase all this. They have in common that they are integrals on the same curve. This curve for which I'm going to use the same parameterization for both. If I'm using the same parameterization, that means that they have the same velocity and therefore the same magnitude of the velocity, namely the speed, namely our stretching factor. So a lot of what we're going to be doing in computing these two integrals, different physical quantities, same curve, same bunch of other stuff, and so these integrals are very, very closely related. Okay, now there's various details in here. Let me highlight these as we go. We've already talked about how mass is density times size. Let's see here. Well, I'll do it like this. Let's see here. ds is speed times dt. It's the same for both. Let's see here. Density, x plus y for both. Again, reminder, we're using the same parameterization, the same blah, 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 and so the range of values of t is the same for both, 0 to 1 and 0 to 1. Everybody okay so far? Now it's just a matter of plugging in the parameterization and the other particulars. Now, again, we've already talked through what our stretching factor is. So this stretching factor, our speed, is that square root in both of them. Don't forget, and let's see, yeah, here we go. Don't forget that the parameterization itself tells you what x and y are. Right? Easy to lose track of this, but this is literally telling you the formula for x as a function of t. And so, boom, x is that, x is that, x is that. That's just coming straight out of that being the formula for x as a function of t. And then likewise, y as a function of t is that. So I'm just literally plugging in, pulling back through the parameterization, as I like to say. And now we've got it down to just plain old boring integral. So this is a Calc 1 integral, and this is a Calc 1 integral, and y'all can crank out the rest of those details. And then likewise for these other examples, they're totally analogous. Take a look through those. Okay, stop here. See y'all later. Have a good one.